So, is quiz 6 the one that I missed on Friday?
Yep.
Okay, and I can take that after class if you want. Or you just audit out of it and just take whatever they got.
Well, I mean, or it could be one of your 2 drop quizzes.
I'll just take it.
Okay.
Yeah, I mean, we're going to take better one of those as well. I will be in class next Friday. I'll be leaving Thursday morning.
Okay, fair enough. Alright, so we left off last time trying to determine a rate equation for production. Right, so we're looking at the velocity of the production of products over change in time, which based on our equation that we had here is related to K2 and ES. So measuring the enzyme substrate combination at any given time is hard because it's dependent on a bunch of other things. So we came up with this equation. And then we're going to choose some experimental conditions to make it easier for us to solve that. Yeah, I have we are way off of the PowerPoints, so you're going to just want some blank paper. But I have to say it's going to fill up way more space than the little PowerPoint has space for. So just go ahead and get yourself a piece of blank paper. All right, so we're going to choose some experimental conditions to help simplify our calculations to determine the production of product. So, first simplification. So when we looked at the graph on Friday, this one over here, all right, there was the enzyme was the limiting reagent, substrate concentration kept increasing, but we maxed out on how much we could make because the enzyme is the limiting reagent. And that will be our first simplification. Make the enzyme the limiting reagent by having the substrate concentration much, much, much greater than the enzyme concentration. Bless you. This way, when we combine enzyme and substrate the concentration of the enzyme substrate combination remains almost constant, because even there's a ton of substrate, there's only so much enzyme that can combine to make this transition state. This is going to be called the steady state concentration, indicating that that ES concentration is constant over a given amount of time. So if I was looking at the change of the concentration of ES over change in time, my DES over DT, if I now have a steady state concentration of ES, what is the change in ES? 0. So now that is 0, which helps us out in a bunch of different ways. The steady state assumption, which is a big deal in enzyme kinetics. Using this steady state assumption, we can say at the rate of ES formation equals the rate of ES consumption. So how is that helpful when we're trying to figure out how much product we are making in the end? So looking back at that original equation we had, this change in enzyme substrate over time, I've now set this equation equal to 0, is what I've done. So this value right here is now 0. So 0 equals this minus that minus that. So I'm going to go ahead and rewrite that, because we're going to work some more with that. I'm going to move around some of the terms, because we're going to look at some of the other things involved in that equation. This is all still Michaelis-Menten. Yep. We got 4.5 pages more notes before we get to big KM. So. Such a big deal, such a huge deal. I'm thinking, what's my next picture? My PowerPoints. Oh yeah, we got a ways to get before we get to letter C. We got a little stuff to work through. Oh, no, sorry. Lost my train of thought. See if I can color code it like I had before. All right, so I set this original equation up here to 0 now. So I put that should be a plus. I've gotten rid of all the minus signs because I left this, I added this to this side, and added that to that side. So now I have one term equals the other two terms. Except, missed my brackets. There we go. So I have K1, concentration of E, concentration of S equals K minus 1, concentration of ES, plus K2, concentration of ES. So I have all the enzyme substrate guys on one side. My brackets look a little funny because I forgot to add them in. So I have all my enzyme substrate concentrations on one side of the equation and my just enzyme, just substrate on the other side. Good so far? Okay. Let's then look at simplification number 2. So the second thing we're going to do to simplify this equation at any given point in the reaction, the concentration of enzyme all by itself, like free enzyme not interacting with the substrate, is difficult to determine. But you're the person who put together the reaction, so you know how much total enzyme you put in there. Right, because at some point you started the reaction, so you put in so much enzyme with so much substrate, so you should know how much total enzyme you put in there. Where enzyme total has to be all the enzyme that's all by itself, plus all the enzyme that's mixed up with a substrate. It's the only two things your enzyme can be doing. So now I have an expression for E I can substitute in up here for this E that puts it in terms of things I know. So I'm going to rearrange this equation. All right, because I'm trying to get the whole equation in terms of things I can measure. So now I have an expression for free enzyme in terms of total enzyme and enzyme substrate combination, which is good because the rest of the equation is in terms of enzyme substrate concentration. So my new equation will be this. Let's see. So all I've done is I substituted this statement of E into this E that was up here. So now we are closer to getting everything in terms of things I can measure or get a good handle on. So the next step I'm going to do to simplify this equation, because it still looks kind of crazy, is I'm going to put all the rate constants on one side and put all the concentrations on the other side. All things that are K to one side, all things that are brackets to the other. So when I do that, Now I have all my k's over here. I divided through, I left this guy on top, I divided that side through by k1, and then that leaves me with divided by concentration of E bracket S. So I did some algebra rearrangement. I am now going to combine terms. All things that are little k are now going to combine. That is now big K. Big K, you know it's a big K because it has tops and bottoms on the K. Big K, little big M. Big deal. We're at the Michaelis constant. Which is, we're getting close, right? Because we're trying to get to the Michaelis-Menten equation. So far we have the right constant. So the Michaelis constant is all the rate constants in the equation. So in this case, it is the rate forward and backward of making the ES combination and the rate forward of making product. So it's a combination of all your rates. Combination of all the individual rates that were in that reaction. So now let's further work on this equation because it's still not great. It's still in terms of at least ES that we don't have a good handle on measuring. So I'm just rewriting the same equation, but now using the Km. What I'm going to do is divide through by this enzyme substrate, right? The only common factor in both the numerator and denominator. So I'm going to divide through top and bottom. In order to do that, I really multiplied out, right? I did this times that, that times that, divide by that. Then I could divide through the ES's, and I'm left with this minus S over here to the side. So we are one step away, right? Because we know the enzyme total, because you put it in there. You know the concentration of substrate, because you put it in there. Km is a constant, so we know that. The only thing we don't know still is this ES combination. So what we're going to do is we're going to rearrange it, put all the things we know on one side, all the things we don't know on the other side. Now I have all the things I don't know on one side, all my constant values over here on my right side. We're getting so close. Very excited. So, let's get this on. So from last time, we had this equation. We had a velocity that related the K2 ES. Because what we're looking for is we're trying to get to a velocity or a rate of how fast we're making our final product. So I'm just going to combine that equation with this equation. So really, I'm just multiplying both sides by K2. Because if V equals K2 times ES, now V equals K2 times ES, which means I then have to have a K2 on the other side of that equation. So now we're going to make a third assumption to help us solve this problem. We are going to measure the rate of the reaction at the beginning of the experiment. During that linear portion of the velocity curve. The velocity curve we just looked at, this one over here. All right, there's a linear portion, and then there's like this tangent portion. We are going to do all our measurements in this first time block, in the linear portion of the reaction. So when we said that we're going to ignore the K minus 2, right, we're going to assume that ES, the E plus P doesn't go back to ES. Right, we made the assumption that ES only goes to E plus P. It's not an equilibrium equation. It's really because of this, because we're only looking at the first little bit of the experiment. There is an equilibrium, but we're only looking at the first few minutes of the reaction. So we're going to assume that it doesn't have enough time to equilibrate back to the to the ES combination. So we're going to call this the initial velocity. This is going to be a super key feature to enzyme kinetics. So no initial velocity. And it is the equation we just wrote. That's going to be one of the equations you're going to need to be familiar with. The initial velocity depends on K2, which is this, the ES going to E plus P, that's K2. The enzyme total, the substrate total, and the Michaelis-Menten constant all work together to figure out initial velocity. So now we can probably use this page if you're back to your PowerPoints. So Michaelis-Menten constant, we've looked at initial velocity. we just looked at, that's V0. Somehow that's not any better. There we go. V0. So the other term we need to know about is maximal velocity, Vmax. So the final assumption we're going to make for this section So we're going to make the assumption that when the substrate concentration is very high, all the enzyme is in the enzyme substrate form because there's tons of substrate, and so all of it will be combined together with some enzyme. That's just rephrased in the steady state assumption. So when we are at that point, the steady state, we are at the theoretical maximum activity. So the equation for that, Vmax, maximum velocity, is equal to the rate of K2 times the enzyme total concentration. Yeah?
Is the initial velocity a small v and the maximum velocity?
A big V. Yeah, so I try to draw them slightly different. The V is more, this is like a big regular V. This is supposed to be kind of an italic-y, scripty V that kind of leans tipsy side. So we now have a new something to put in our equation. Yay, right there. So we're going to sub that back in. So now, Vmax times substrate concentration divided by Km plus substrate concentration equals the initial velocity. That is the Michaelis-Menten equation. So there are 4 major assumptions that you have to make in order to get to this point, which is why we have to walk through all those steps to get here, because there's some big things you have to assume are true, which usually true. So let's flip back one PowerPoint and we'll look at that graph. This one. Does everyone have that part? Michaelis-Menten equation. Okay, so let's look back at this graph that is concentration of a variety of things. Let's zoom in. Okay, I think everyone's just about done writing, so I'm going to move this way. All right, so let's look at this graph. It has concentration. And it's not labeled concentration because I'm both going to look at enzyme total concentration and substrate concentration on this graph. So here is my enzyme total concentration. Here is my substrate concentration. All right, substrate concentration initially is much, much, much greater than enzyme total concentration, where enzyme total is equal to free enzyme plus enzyme substrate combination. So this is time increasing, going to the right. So at the beginning of my reaction, I have a little bit of total enzyme. I have a lot of initial substrate. As the reaction progresses, the amount of free enzyme I have decreases, right? Because free enzyme plus the substrate, the free enzyme concentration has to go down. Let's see where I want to put this. So as the reaction starts, concentration of free enzyme decreases, then plateaus. All right, quick decrease, and then it maintains a steady state concentration. The concentration I have of my enzyme substrate combination increases the opposite slope of what free enzyme was. So all the stuff that was free enzyme is now hooked up in my enzyme substrate combination. So the concentration initially increases, then we're in the steady state. That's why this area is shaded in gray. That is the steady state assumption right there, that the amount of free enzyme I have is steady, the amount of enzyme substrate combination I have is also steady, which means that everywhere in this gray shaded area, the concentration of ES over change in time has to be 0. So this gray shaded block is my steady state. Steady state. That's kind of crazy looking. All right, the last 2 points to look at are substrates and products. So as the reaction starts, all right, I had initial concentration of substrate that is decreasing with increasing time, which should make sense, right? You're using it up to do this reaction. So then my concentration of products has to increase as the reaction heads forward. So that's not nearly as interesting as the other parts, but true. I mean, it's true. That as the reaction starts, free substrate decreases, free product has to increase. So then let's take that information and plug it back into wherever I just had that. Oh, over here. Here we go. All right, so all the information about that graph, how it's related to this. There's the rate equation for an enzyme catalyzed reaction. And for this equation, what do you think you plot on the y-axis? Thinking of a regular old graph, what part of the equation goes on the y-axis? Yeah, V, right? This is like I'm saying y equals an mx plus b. It's not exactly right, so we're going to plot V0 as my y versus substrate on the X, right? Because substrate's my independent variable, so that goes on the X. This is my dependent variable, so that goes on the Y. So substrate concentration versus V0. And what do you know? That's what you've already plotted. So anytime you plot that, it's going to be this shaped curve, where now this max reaction velocity is Vmax. That is, we've already pointed it out, we just mathematically described it. So now, this max reaction velocity is equal to K2 times enzyme total. That's this guy. Reaction velocity, all. So then this part is the V0 portion of it. Have I blown everybody away yet? Getting there? So, you may be thinking that Michaelis-Menten constant, this big guy right here, this Km, it's a little tricky because it's made up of other rates. So what are some things that we need to know about that guy? Because it's a constant, but it's made up of other rates, kind of a confusing thing. And how do I know if it's a good constant, like if it's a good enzyme, fast, or if it's slow? Well, I'm glad you asked. So just a reminder, Km is combination of rate constants. So it is a rate constant, but it's made up of other rate constants. It only occurs when you're at high substrate concentration and enzyme is saturated, because those are the assumptions we have to make in order to find Km. When we're at a concentration where numerically concentration of S equals the Michaelis-Menten constant, we are now in a spot where here's my Michaelis-Menten equation. All right, initial velocity equals Vmax times S, Km plus S. If I'm numerically at a spot where Km equals S, that would be true. You're now at V0 equals Vmax over Km, because I'd now have S over 2S. So the top S would cancel out. I'd still have a bottom S, or Vmax, or sorry, Km. That's the point at which V0 equals 1/2 its maximum value, graphically. So we want to look back at that. Actually, if you go ahead one slide, I have it on the next slide. So it's the exact same slide we had a bunch of slides ago. But now substrate V0, or V on this axis, Vmax is still where it plateaus. Where you're at the half maximal velocity, that is numerically the Michaelis-Menten constant, which means graphically you can determine the Michaelis-Menten constant even if you don't know it for that particular enzyme. This is how you'd go about finding Km for a particular enzyme. Bunch of good things about Km. Why we care about Km is that we use it to compare how good your enzyme is at selecting a substrate and converting it to product. So we use Km to see how much substrate do you need to get to that Vmax 1/2 or Vmax, which is an indication of how efficiently the enzyme is able to do that. And Km is unique for each enzyme substrate pair. So looking at my x-axis here, right, if that's concentration of substrate, where Km equals S from at 1/2 max, which tells me about Vmax, if I have a low value of Km, that tells me that my enzyme substrate pair is very effective. Right, that means a low concentration of substrate doesn't need very much substrate in the solution to make the correct product. If I had to have a lot of substrate, that would tell me it's less effective at doing it. So if I have a low value of Km, it is more effective at finding the one substrate in solution that it needs to make the right product. Then the opposite would be true.
Means that the substrate is more effective or that the Km is more effective?
The enzyme is more effective. Yep. Yeah, the enzyme is more effective at seeking out the right substrate to make the right product. And we can also use to compare enzyme substrate combinations as to how effective they are. How's everyone feel about that? Yeah. All right, we'll look at this little tiny chart, and then I will save KCAT for Wednesday. So here's my table of KMs. There's a lot more information on here. We'll get to KCAT and KCAT over KM. But so carbonic anhydrase, it has 3 different things it could possibly react with. And you can see that it is more selective for carbon dioxide than it is for carbonic acid or hydrogen peroxide, which is good because it should be reactive with carbon dioxide. Or we could look at fumarase, which is an enzyme we'll look at in more detail, I think, next chapter. Fumarase can react with fumarate or malate, and is much more selective for fumarase, which is its correct substrate, than it is for malate, which is the incorrect substrate, but does fit into the active site. And so we can use this to kind of compare how effective the enzyme is for reacting with its correct substrate to make the correct product. All right, now that I've totally blown everybody away, we'll stop there.